meters per second squared, is equal to big G, universal gravitational constant, times the mass of the object producing the field over the distance from the center of the mass, all squared. Okay. Big G is a constant on your formula sheet. It should be at the back. So that's always a constant. And we are going to be able to find the gravitational field strength with different on different masses, like different planets, things like that. Okay, so this little g on Earth is negative 9.81, but not meters per second, but not other places. Big G is a constant though, and that is found on your formula sheet. Okay, so let's look at example number 1 here. We have the planet Mars has a mass of 6.42 times 10 to the 23 kilograms and a radius or distance from its center as 3.38 times 10 to the 6. So you can see we have a mass, we have the radius, and we're going to use big G, that universal gravitational constant, to find our little g. Okay, so that is just what I did here. I wrote the formula and then I put in the values. Let's look at what's going to happen here. And feel free, this is a video, so to pause, to write things down. You can see that we have kilograms squared, kilograms on the top, so we're going to be left with kilograms. We have Newton meters squared divided by meters squared. So let's see what's going to happen there. We have newtons per kilogram. Now, what was a newton? A newton is a kilogram meter per second squared. So when I say I have a newton divided by a kilogram, so here's a newton, and I divide that by a kilogram, what's going to happen? Kilograms divided by kilograms cancel out, and I'm just left with meters per second squared. So a newton per kilogram is really the same as a meter per second squared. So just know that as your units come out, you're going to be okay. So rewatch that if you didn't quite follow what I did there. So I actually put this in my calculator, 3.74 with some change, rounds up to 3.75 meters per second squared. Okay, it's really important that you're able to get these correct answers, these times 10 to the negative 11 times 10 to the 23, that you know how to use your calculators. We're always going to have funny numbers like this. So on your calculator, you're looking for a button. It might look like this, EE. That's how you do 10 times 10 to the. Or you might have a button that says EXP. Either one, play around with and see if you can get this correct answer. If you absolutely cannot, please send me a photo of your calculator and I'll help you figure out how to enter it in. Okay, the other thing you could do is you could ask a science or math teacher to help you out as well if you're having calculator troubles. Okay, now it says determine the weight of a 60 kilogram person on Mars. So force of gravity is the same as weight. We're going to go mass times this new g we just found, the new acceleration due to gravity. Okay, so 60 kilograms is how much that person weighs. We're going to times it by the rounded version, and we are going to get, when we go kilograms times newtons per kilogram, we're left with just newtons, and when we round that we get 225 newtons. How does that compare to his weight on Earth? Well, on Earth it should be 9.8 or 9.81 newtons per kilogram, and I got him to be 588 newtons is his weight. So you can see he weighs less on Mars. Okay, finally determine how that 60 kilogram person would feel as an apparent mass in kilograms on Mars. Their true mass never changed. They're still going to have the same amount of stuff, but the person will feel lighter on Mars than he is used to gravity on the Earth. So what we do here is we say F of G. So to find out what is F of G feels like, Fg equals mg. So to find his mass, so we go Fg, which was 225 we just found, divided by the G on Earth, 9.8 or 9.81, depending on which resource you use, and 229 kilograms. So he would feel just like he only weighed 22.9 kilograms instead of 60 kilograms. He would feel a lot lighter.